Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the third lecture of your online lecture series, your lecture number 27, and in this lecture we will continue with your operational amplifier circuits and their application and their design examples in the signal conditioning, analog signal conditioning circuit design. So let's get started. Before moving on to the application circuits of the operational amplifiers, let's solve an example in which we are going to design a basic signal conditioning circuit for one of our sensors. So the statement of the question is that the sensor output is in terms of voltage, and that ranges from 20 millivolts to 250 millivolts, or you can say 0.02 volts to 0.25 volts. Whatever parameter this sensor was sensing is not of our concern right now. What we are interested in is the form of output of that sensor, and that is voltage, and the range of that output voltage that is given to us, that is from 0.02 volts to 0.25 volts. Now let's assume we want to convert this voltage to a value so that it can be easily integrated with a 5 volt ADC. So the ADC input is usually from 0 volts to 5 volts. So what we want to do ideally, to utilize the full range of ADC and the full precision of ADC, we want to convert this 20 millivolts to 250 millivolts from this value to 0 volts to 5 volts. Normally, in case of operational amplifiers, what we know that the V out is equal to MV in plus V naught. This V naught is not V output, this is the offset. So let's make two equations of that. We have a known V in, but we have an unknown slope and an unknown offset, and if we are able to find these two unknowns, the slope or the gain of the amplifier and the offset that is required for this circuit, we will be able to implement an operational amplifier based signal conditioning circuit that will convert this range of inputs to this range of outputs. Now let's see what was our required output when our input was 20 millivolts. Our required output was 0 volts and our input was 0.02 volts. And what was the offset required? We don't know yet. And then let's call it equation 1. The second information we already have is that for 250 millivolts or 0.25 volts, M into 0.25 plus V naught, our desired output voltage is 5 volts. So let's call it equation 2. Now we have two equations and two unknowns, M and V naught, the offset. So simultaneously solving these two equations, we get M is equal to 21.7 and the offset V naught equal to negative 0.434 volts. And let's put these two values back in our parent equation, and we'll get our V out is equal to 21.7 V in plus 0. Or let's change it to minus 0.434 volts. Now this is the expression that we want to implement using operational amplifiers, and that is fairly simple. We can simply assess from this equation that our V in needs to be multiplied with a gain of 21.7, and then after that a 0.434 volts has to be subtracted from that. Another way of writing this equation can be V out is equal to 21.7 into V in minus 0.02. Both these equations are same. I've just taken the 21.7, the gain, common from the input and the offset. So what we can do is we can first subtract a 0.02 volts from the input voltage, and then that result of subtraction after subtraction can be multiplied with a combined gain of 21.7, or we can first multiply our input voltage with a gain of 21.7 and then subtract 0.434 volts from the output of the first stage. You can do whatever you want. You can implement whichever equation you like. So let's see what should be the circuit that will be used to implement this equation. So just for the sake of randomness, let's implement this second equation. So what we want to do is, because this expression V in minus 0.02 is inside these brackets, so automatically this becomes the first stage of our circuit. So what we want to do is we want to subtract 0.02 volts from our input voltage. So let's apply an input voltage at the positive terminal and apply a 0.02 volts at the negative terminal. We'll keep modifying this circuit, but just for the sake of it, let's do it like this first. We want to make a difference amplifier. So here is 0.02 volts. It can be coming from any fixed voltage source, and here is our V in. And then after the first stage, this output needs to be multiplied by a gain of 21.7. So if we use a non-inverting amplifier, the formula for gain is 1 plus R2 over R1, and we need a positive gain here, so we don't want to invert our signal. So let's make a non-inverting amplifier, and like here at the inverting input we connect a feedback. We'll come back to this part later. This R2 is equal to 20.7 kilo ohms, and this R1 is equal to 1 kilo ohms. And you can see that R2 over R1 is 20 over 1, that is 20, and 1 plus R2 over R1 is 21.7. So again is being given to whatever input is coming at this terminal, and that is a non-inverting amplifier. So this part of giving a gain of 21.7 is completed right here in the second one. But is this one correct? This circuit, this portion, there is no feedback, so it is giving the open loop gain to whatever the difference is, and that is almost infinity. So we have to connect some sort of feedback to this circuit, and for that we have to design a difference or differential amplifier where the gain is 1, but we only take a difference of these two values. So what I'll do is I'll just replace this whole block with a difference amplifier, and a difference amplifier with some buffers. So this is a unity gain buffer, because in case of a difference amplifier we know that there is effect of loading, and when there is loading on 20 millivolts, it will be further reduced and will result in enormous errors in our reading. So now this is our V in, and this is our 0.02 volt offset V naught or 0.02 volts. And then this is the input of a difference amplifier here. So this is positive, negative, and a feedback here, and a ground here. So this, let's put all these as R's. Doesn't matter what value these resistors have. So it will just give a gain of 1. This is a difference amplifier. V in minus 0.02, V in minus 0.02 into R over R. That is the gain of this difference amplifier, that is 1. And then, so this is the output at this stage. And then multiply all this by 1 plus R2 over R1, and that is equal to 21.7. So at the output we get 21.7 into V in minus 0.02. So this is one of the simplest signal conditioning circuits that we can design. So I hope now you know that which steps do we have to follow by converting a simple voltage range from one set of values to another set of values. We develop equations, we solve the equations, we find the unknown parameters, and then we develop a final relationship between the V out and V in, and we will probably have some offsets and some gains that we can easily manage through by using different configurations of the operational amplifiers. Now after this, let's come to the application targeted configurations of operational amplifiers, and those include current to voltage converters, voltage to current converters, and the differentiators, integrators, linearization circuits, and so on. So we'll start with the simplest one, that is current to voltage converter. What is a current to voltage converter? As the name states, that it converts a specific magnitude of current to a specific magnitude of voltage, and the input current and the output voltage can be related through a mathematical equation. So our target is to relate the output voltage with the input current. Let's say you have some circuit whose output is current, and that current is I. So let's connect it with the negative terminal of an operational amplifier. Now we know that no current can flow through the inputs to or from the inputs of an operational amplifier. So where will this current go? We have not provided any path for this current to flow. So let's provide it a path, and that path would be a feedback path, and that is R. Now this current will pass through this resistor R, all of this current. No current will flow here. I is equal to 0 here. And just simply ground this other positive terminal. We could have just simply grounded this positive terminal without a resistor. I'll come back to that, why we did put a resistor here. But for now, let's assume that there is a resistor. Now we know that as no current flows through this negative terminal, all the current is passing through this resistor, and this V out is equal to I into R. And now we have a relationship. This resistor R, we are putting it ourselves in that circuit. So this resistor is a known resistor, and when we know the value of this R and we can measure the V out, we can easily find out the input current, that is equal to I is equal to V out over R. So we have a physical relationship between this voltage and this current. Now this resistor R, this second resistor R in the non-inverting terminal is added to provide temperature stability to the configuration. This temperature stability can be explained when we used to add an emitter resistor in our BJT circuits. If you remember that in electronics 1, you used to add an emitter resistor, and that provided temperature stability to the amplifier circuit. That remember, that was also a transistor acting as an amplifier. So the proof that how this R gives a temperature stability is provided in your electronics 1, and you have already studied that. Just here I am using that concept again. What if you don't connect this R to the ground? You just connect you just ground it directly, you just short circuit it. It will not affect anything, but if the temperature varies in your surroundings, there can be errors in your output reading. So it is recommended to use this R, but if you assume that the temperature of your surroundings remain constant, you can even skip this, and you can just simply ground this terminal, and it would have no effect on the output relationship. So this is one of the most simple examples of the application targeted op-amp configurations. The question arises, why this op-amp? We are only doing V is equal to IR. So what if I just had this circuit that my current was coming I, and I just connect a resistor R and convert it into a voltage V out? Why not doing this? The current will flow through this resistor, and a voltage will drop across this resistor, and that would be V out, and that would be equal to IR. So why connect this op-amp? Isn't it useless? Why can't you simply convert this current into a voltage by simply passing it through a resistor and taking the output voltage? Try to answer that. I'll give you 5 seconds to think about that, and then I'll answer it myself. What is the purpose of op-amp? What were the characteristics of op-amp? Think in those terms. Okay. An op-amp characteristics are that its input impedance is very high or close to infinity. So the op-amp does not act as a load on the input, and an op-amp output impedance is very low. So it can provide voltage or current to any output, any other third stage system, and that system will be unable to load this op-amp's output unless and until the V saturation or I saturation of this op-amp, its physical limitations are not reached. So when you are mirroring this V out, or you are providing this V out to an ADC, let's say, let's connect an ADC here, let's connect a load here, and now you can see that this ADC is acting as a load on this V out, and now this R is parallel to the RADC, and now this V out will no more be equal to IR, but I into R parallel to RADC. And you don't know the RADC. So you don't have an accurate relationship between your voltage output and your current input. So your calculations are wrong. What about in this case? V out is equal to IR. Connect an ADC here and let's see what happens. Nothing happens, because as far as this op-amp is able to provide the current to drive this ADC, it will not act as a load, and V out is equal to IR will remain a valid expression. So it is very crucial to convert the current to your voltage and use an op-amp, not just use a passive circuit. I hope this will clear this concept. Now let's move on to the voltage to current conversion. We discussed the current to voltage conversion. Now let's come to the to a bit more complicated voltage to current converter, and again we'll start with the very basic one. Okay, so here we have our circuit, our basic circuit for voltage to current conversion. As we know that I1 is equal to I2 because no current flows in or out of these terminals. This implies that I is equal to VI over R1. I think we can all agree to this. Now, this current I is independent of your R2 and your RL. Whichever load resistance you connect at your output and whatever R2 is there does not affect the amount of current flowing through this circuit. So we have successfully converted our input voltage to an output current, and that output current can be taken here. But this configuration is not very practical because now this RL is not our actual targeted load from which we want to pass a fixed known amount of current, but rather this is our load from where this I is passing. Through this RL, we don't know the amount of current passing. We want a known amount of current to pass through our load. So this is our load. And you can see that both the terminals of our load are at some potential, some non-zero potential. No terminal of our load is grounded. So normally in practical considerations, our load has to be connected between a ground and a positive potential or a negative potential. There has to be a ground terminal in most of the cases. In some cases it is even possible. That's why I am even discussing this configuration, because for very rare applications this configuration can be used. A load can be connected in between this feedback loop, but usually it is not a feasible solution. So what we have to do to tackle that? There is another configuration, a more complex configuration, to convert our input voltage to a known output current, and that known output current should be able to drive our load regardless of the load resistor. If the current is changing based on our load resistor, it is useless because usually we do not know the system resistances. Our load is usually a system, and we usually do not know the system resistances, the input and output resistances. Any type of load in a range should be able to be connected to our current source or voltage to current converter. So let's draw that circuit and let's see how it works. So this is our circuit. Here is our V in. This is R1. This is R2, R3 and R4. And this one right here is your load. It can be impedance, it can be resistance, whatever. That's why I wrote ZL, because regardless of whether it is a simple resistive load or even a capacitive or inductive load, we don't care. This circuit will be able to manage that. And then this is our I4 and this is our I4 IL, the current flowing through the load, and this is the current in which we are interested. So let me highlight it. And then this is our I1, this is our I2 and this is our I3, and this is our V out. So this is V negative and this is V positive, and we know that I is equal to 0 here because it is directly connected with the input terminal of the op amp. Now let's try to derive this relationship. First, let's see what is the value of this V plus and V minus. Is it 0? No, because both the positive and negative terminals are not grounded. If even one of them was grounded, we know that V positive is equal to V negative. So if even one of them was 0, the other one was automatically 0 as a virtual ground. But this is not equal to 0, and this is equal to what? Let's find out. And for that, we'll have to solve this circuit. So let's start by finding out these currents. I1, what is I1? I1 is equal to Vi minus V1 or Vi minus V neg over what? R1, the current flowing through resistor 1, and that is equal to what? Now, what comes at this question mark? We have to find it out to proceed with these calculations. What is this potential VL here? VL is equal to ILZL, the current flowing through the load. And are these in parallel? Yes, they are. So this is equal to I4 R4. So what is the potential at this point? V is equal to ILZL or I4 R4. And isn't it directly connected to the positive terminal? Yes, it is. So we found the potential at one input of this op amp, and as they are equal, this means that they are both equal to ILZL. So now I can replace this V neg with Vi minus ILZL over R1. Now coming to the second current, the current through resistor R2, that is I2, is equal to V neg minus V out over R2. V neg minus V out over R2, and that is equal to ILZL minus V out over R2. But we know that I1 is equal to I2 because no current flows into this negative terminal. So this means that Vi minus ILZL over R1 is equal to ILZL minus V out over R2. So this is our equation 1. Now coming to I3 and I4. As no current is flowing through this, so I4 is the current passing through R4, and I3 is being divided into IL and I4. So this at this point, if we apply the KCL, we find out that I3 is equal to I4 plus IL. This implies that what is the value of I3? I3 is V out minus VL, right? V out minus VL over R3. So V out minus VL over R3 is equal to what is I4? I4 is the potential at this point, VL minus 0 over R4. VL minus 0 over R4 plus what is IL? Again the potential at this point, VL minus 0 over ZL. VL minus 0 over ZL. Let's call it equation 2. We have a relation linking the V1, IL, ZL and R1 to V0, IL, ZL and R2, and then we have a relation linking V out, VL, R3 and with R4 and ZL. let's write this VL in terms of the current in which we are interested in the load current. So let's rewrite this equation 2 to V out minus ILZL over R3 is equal to again ILZL over R4 plus VL over ZL is IL. So this is a really important equation that will help us to finally derive the expression or the relationship between our input voltage and the load current, and that load current is independent of the ZL. So let's rearrange this equation and see what happens. V out is equal to IL ZL plus R3 over R4 into IL ZL plus R3 into IL. Let's call it equation 4. And now rearranging equation 1, we get R2 over R1 into Vi minus IL ZL minus IL ZL is equal to negative V out. Now equate these two. Put the value of V out from equation 5 in equation 4 and you will get R2 over R1 into ILZL minus Vi over R3 is equal to IL plus ILZL over R4, or you can say IL into RL R2ZL over R1 R3 minus 1 minus ZL over R4, and that is equal to Vi R2 over R1 R3. Now this expression highlighted in blue is linking our input voltage with our load current. There is no other voltage or current in there. There are only the resistors that we are using in our circuit and the load resistor. So one of our two targets have been achieved. What were the two targets? To relate the input voltage with our load current, and we have successfully related them independent of the other voltages or currents present inside our circuit. There are just some values of resistances R1, R2, R3 and R4, and that are selected by us. The second target was that this relationship of Vi and IL should be independent of the load resistor. But here we can see that the second target has not yet been achieved. ZL is still present in our expression. So what we can do to make this expression independent of the ZL? This will become independent of the ZL when the coefficients of ZL will become 0. And when will it become 0? Here is a positive sign and here is a negative sign. And to make this expression 0, we have to set R2 over R1 R3 equal to 1 over R4. So if this condition is true, the factors of ZL will be cancelled out and the current will become simply IL is equal to negative Vi into R2 over R1 R3, independent of the load resistor. So this means that to make a good voltage to current converter, we have to satisfy this expression always. to keep the ratio of R2 over R1 R3 equal to 1 over R4. RL minimum may be equal to 0. The range of the load resistor is being defined here. So this is just one part of that load resistor range. The second one is actually a limitation, the upper boundary of our load resistor. So RL maximum has a certain limitation, and that is defined by this expression R4 plus R5 into V saturation over I maximum minus R3 over R3 plus R4 plus R5. You can see that in our circuit there is no R5. So we can simply replace the R5 by 0 in this expression for our circuit. So the expression will become R4 into V saturation over I maximum minus R3 over R3 plus R4. Your load must not exceed this value. What is V saturation? The saturation voltage of the op amp to the maximum value that can be attained by the operational amplifier at the output. What is the Imax? The maximum amount of current that can be supplied by the operational amplifier. If you connect a load greater than this value to this circuit, either the voltage will saturate or the current will saturate. So you have got a range for your load, the minimum and maximum value of the load that can be connected to this particular circuit of voltage to current conversion. Now coming to where these circuits are used. We have discussed the current to voltage converter and voltage to current converter. Current to voltage converters are extensively used in many applications where your transducer provides an output in the form of current and you want to measure it. And to measure a current, you usually convert it to voltage first and then measure the voltage, and then based on that expression between the output voltage and the input current, you find the unknown parameter. Secondly, it is used in signal transmission. We discussed in our class that in industry the signal transmission standards are not based on voltages but rather currents. So the signal, whatever signal is there, is converted into current, is transmitted from one point to another point, and then it is converted back into voltage. So this current to voltage converter and voltage to current converters are used in signal transmission at the transmitter and the receiver end. So this means that this current to voltage converter will be put at the receiver end, and this voltage to current converter will be put at the transmitter end. So one application of the voltage to current converter is also discussed, and in other cases there are appliances, there are inductive appliances especially, that need a constant or a known current supply to operate, not a known potential. So we have to provide a known current to those devices to correctly operate them. And in those applications, as our driving circuits are usually voltage based, so we generate a known voltage and we convert it into a known current and then connect our load that has to be derived with a known current. So there are further applications. You can explore them by searching them out and by reading in detail your textbook. The basic idea of this practice we are doing right here is to give you an understanding of how it works and how these things are related. So now we have covered two of the very important application based configurations of operational amplifiers, and we are nearing completion of these op-amp circuits and op-amp configurations. So let's move on to the next three, the last three, and we'll quickly go through them because you have already covered them in your previous courses. So I'll not go into the detailed derivations of the coming circuits, but just give you a revision of the basic concepts, and then we'll move on to our design example. Now quickly coming on to the remaining three configurations, application-based configurations of operational amplifiers. We are going to discuss the integrator, differentiator, and linearization. So let's start with integrator. You have already studied the integrator circuit in your previous courses. Let's draw a circuit of that is basically an inverting integrator, where we have the input at our inverting terminal, and instead of this feedback resistor, we have a feedback capacitor, and similarly the other things are same. So this is our VI, V out, and the positive terminal is ground. This is R and this is C. So as we know that the current passing through these two branches is same, as no current goes in or out of these terminals. This means that V in over R is equal to negative C dV out over dt, the current passing through a capacitor. If we integrate these two, integration of dV out over dt is equal to integral of negative V in over R, and this implies that this gives our V out to be equal to negative 1 over RC integral of V in dt, and this means that our input is being integrated at the output with a time constant of RC, and the transfer function of this integrator is V out in S domain over V in S domain, and that is equal to negative 1 over SCR, or you can say, if we just take V out over V in, the magnitude, that is equal to 1 over 2 pi FCR, and you can see that it is similar to negative R2 over R1 or negative Z2 over Z1. And these integrator circuits can be used to implement analog controls, control systems like PIDs. Mostly now those systems have been shifted to digital systems, but still in the modern day, these circuits can be used, the integrator circuits can be used to generate highly linear ramps, voltage ramps. The second circuit we are going to discuss here is the differentiator. Again, you have studied the differentiator before, so let's quickly go through that and make this circuit. It is also an inverting amplifier, but just different from the integrator in a way that now that capacitor is replaced with the resistor and the resistor is replaced with the capacitor. So these two have interchanging positions, and the capacitor is now at the input and resistor is now at the output. And just by changing this and just by visualizing it, you can see that the effect would be opposite. Previously, the output was being given as the integral of the input. Now, the integral of the output would be the input. So, the derivative of the input would be the output. So, let's see, I is equal to C dVi over dt, and that is equal to the output current, that is negative V out over R. So this gives us V out is equal to negative RC into dVi by dt. The response of differentiator circuits is usually unstable or erratic, and this has many applications, and plus one common application again in the control systems, and again that is not widely used in these modern days, where better techniques have been developed to generate unstable or erratic circuits. The differentiator circuits can still be used and are still being used. The third one is linearization. Linearization is achieved by placing an opposing or opposite nonlinear element in the feedback loop. For example, if your circuit has a response like this and you add an opposing response like this, you will get a linear output. So for exponential signals, that is usually achieved by, or logarithmic signals, it is achieved by placing a diode in the feedback like this. Let me explain how this circuit or this configuration works. So this is your Vi, this is the current I, the resistance R, and this block in the feedback is a function of V out, where this is your V out. Now we know that V in over R is equal to negative I into V out. And if this is a non-linear variation of current with voltage, the V in is a non-linear variation of current with voltage, V out is equal to G into V in over R. So this is a non-linear function. In case of a diode, I V out is equal to I naught e raised to power alpha V out, where I naught is the amplitude and alpha is the exponential. That is the exponential. This is derived from the Shockley's equation, and we know that the response of diode is like this, the Shockley's equation. So if a diode is in the feedback, we know that our V out will behave in this way: log C into V in minus 1 over alpha log E into I naught R. Alternatively, if we consider the exact equations where I is equal to Is e raised to power Vf over eta Vt, here Vf is the voltage across the diode and Is is the diode saturation current, that is a constant, and eta is the temperature coefficient, that is a constant. This will mean that log of I is equal to log of Is plus Vf over eta Vt. And from here you can see that Vf is equal to eta Vt into log of I minus log of Is. Again, the almost same expression will be derived. So this means that our V out will be equal to negative Vf, and that is equal to negative eta Vt into log of I minus log of Is, where I is equal to Vi over R1, and that is equal to I1. So this implies that your V out is equal to negative eta into Vt into log of Vi over R1 minus log of Is. Is is the saturation current, and that is a constant. So Hence, this is a logarithmic linearization of an exponential input voltage Vi. Vi is a nonlinear exponential input, and a log is being taken of that at the output end. These factors are also contributing in the output voltage, but our focus should be on this particular term, where the exponential input, the log of exponential input, is being taken at the output. And here in this feedback block, in this feedback block, you can use any function that is opposing the function of your Vin, and you can linearize it. A better way to linearize these days is to implement the equation of that particular input and solve it mathematically inside a microcontroller or a microprocessor, because now the digital processing power of basic microcontrollers has substantially increased, and we don't need these kind of circuits much so often. Yet these circuits are still being used, especially for the sensors having exponential output and providing an integrated and cost-effective and miniaturized integrated solution to get a linear output, where a parameter, changing parameter linearly, results in an exponential change in the output of that sensor or a transducer. So these are the basic concepts that are related to the operational amplifiers. Now let's move on to the basic design rules, where you will be designing the analog signal conditioning circuits. So let's go to our slides and let's discuss those basic parameters and the requirements and the step-by-step guidelines, the measurement objectives, etc. Okay, so here are the basic guidelines for analog signal conditioning circuit design. You have a process, and in that process, a change in variable results a change in some other parameters. Those parameters are detected by a sensor, and some intrinsic properties of the sensor change in a certain limit, and that limit is Ymin to Ymax. That this Ymin and Ymax can be a function of capacitance, resistance, voltage, current, or anything. And then we pass these Ymin and Ymax through our signal conditioning circuit. We give some gain, we subtract or add some offset to that, we filter it, we do some processing or conditioning on these variables. We convert these variables from one form to another form, resistance to voltage, and so on, and then we finally get our desired output, that is Bmin to Bmax. So what we have to do? First, we have to define the measurement objective. Defining the measurement objective includes determining the parameter and determining what is the nature of the measured variable, that is pressure, flow level, voltage, current, etc. What is the range of that measurement? For example, 2 to 4 volts, 25 to 96 degrees Celsius, and so on. What is the desired accuracy of our output, and not actually our output, the desired accuracy by which we have to measure that particular parameter? How much tolerance do we have in determining that parameter, the magnitude of that parameter? Linearity. Must the measurement output be linear, or is it not necessary? And the noise, what kind of noise is present, if there is any noise, and what are the level and frequency of the noise? And then we have to, based on those objectives, after defining those objectives, we have to select a suitable sensor, if applicable, if we are measuring some quantity. And to select a sensor, we have to first determine the parameter and the nature of sensor output, whether the sensor after detecting the target parameter results in the change in sensor's resistance, voltage, current, or whatever quantity. What is the transfer function, or what is the relationship between the sensor output and the measured variable? What is the time response of the sensor, first order, second order, damping, exponential, or and so on? What is the range of the sensor parameter output given for the measurement range? For example, for a change in temperature of 30 to 70 degrees, a temperature sensor's resistance changes from 200 ohms to 2 kilo ohms. What is the power specification of the sensor? What is the maximum allowable current? What is the maximum power dissipation, and so on? And then, after determining these parameters and selecting a suitable sensor, we come to designing the actual analog signal conditioning circuit. And the first step in that is, again, the parameter. What is the nature of the desired output? The most common is voltage, as we discussed earlier, but in some cases current or frequency is also preferred, and in that case we can use the conversion circuits, conversion to voltage or conversion from voltage. What is the desired range of the output? For example, in case of the ADC, we said that we need a voltage output from 0 to 5 volts, or in case of the signal transmission in industry, as we discussed that the signal is usually transmitted in terms of current, so the current should be in range of 4 to 20 milliamperes, that is the industrial standard. And then what is the input impedance, what is the output impedance of the first stage and the second stage and the third stage? All the multiple stages that are interconnected, we should know, and we must very carefully consider the input and output impedances of each stage and their effect on the previous and the next stages. So there are some notes on the signal conditioning design that can be helpful. For example, if the input is a resistance change and a bridge or divider must be used, make sure you consider the effect of output voltage nonlinearity with resistance and the effect of current through the resistive sensor. For example, if you have a potential divider circuit, so this is R1, this is R2, and this is V out. V out is equal to V into R2 over R1 plus R2, and I R2 is equal to V R2 over R2. This means that some current is passing through your resistor, your sensor, that is a variable resistor, and this output voltage that you are getting as the output of your signal conditioning circuit, or bridge, or a potential divider, has a non-linear relationship with your change in resistance, but that change in resistance was linear, so that non-linearity has to be considered, and the amount of current passing through this resistor has to be, or your sensor has to be considered. For the op-amp portion of the design, the easiest design approach is to develop an equation for the output versus the input, just like we did in our previous example. And from this equation, it will be clear that what type of circuit may be used. For example, we used a simple difference amplifier and a non-inverting amplifier for the gain. The equation represents the static transfer function of the signal conditioning circuit, not the dynamic transfer function. So always consider any possible loading of voltage sources by the signal conditioning, such as loading in case of when the input is not directly provided at the positive or negative terminal of the op-amp, but is provided through a resistance, because loading is a direct error in the measurement. And to demonstrate these design rules and to actually follow these step by step, let's solve an example of your textbook. This is the example number 24, and here our statement is that you have a sensor that outputs a voltage in a range of 2.4 to 1.1 volts, negative 2.4 to negative 1.1 volts. But to interface it with an ADC, this voltage or any voltage has to be converted to 0 to 2.5 volts. So what we have to do is we have to develop a signal conditioning circuit for this particular application. Convert one range of voltage to another range of voltages. First, for this type of problem, no information is provided about the measured variable, the measurement environment, or the sensor. We are simply asked to provide a voltage to voltage conversion. Since the source impedance is not known, it is always preferred and it is always a good design practice to assume that it is high, and we should design a high input impedance system to avoid the loading. If it is known, then we can decide. If it is not known, we should always be careful and we should follow the good design practice. Most ADCs have input impedances of at least tens of kilo ohms and the output impedance of the op amp is quite low. So there is no real concern for the output impedance of the signal conditioning system, because the output is being taken from the op amp directly. So for this type of problem, it is easiest to develop an equation for the output in terms of the input, as we discussed earlier and as we solved in our previous example as well. So from this circuit, it can be envisioned that V out is equal to MV in plus V naught. Now making two equations, the range of input and using the range of input and the range of output, 0 is the desired output when negative 2.4 volts was the input and 2.5 volts was the desired output when negative 1.1 was the input. And this M is not milli, mind it, this is the slope M, or the gain you can say. Now simultaneously solving these two equations, we get V naught is equal to 2.4 M and we get the values of M as 1.923 and V naught equal to 2.4 into 1.923, that is 4.615. So this is the transfer function of our final desired signal conditioning circuit that we have to design. Now this is fairly simple. It is just like the one we used in our previous example. So there are many ways to satisfy this equation. A summing amplifier could be used, but mind it, it does not have a high input impedance because the input is provided to the terminals of the amplifier itself through resistors. So a voltage follower would be needed at the input. Also the summing amplifier inverts. So an inverter would be required for the correct sign of the output voltage. So here is the circuit. First stage is for reducing the loading effect. Then this second stage is providing a gain of 1.923 as given in this equation, and then the third stage is providing an offset of 4.615 and giving a gain of negative 1. So this is a gain of negative 1.925 and again this is a gain of negative 1. So negative into negative is positive, so your V out would follow this same equation like here. If the design has to be accomplished in a different way like we did in our previous example, we can take the 1.923 gain as common and we can implement it in the way that we already did. So a voltage follower would still be required at the input, and let's make this circuit, and this is the simulation of the circuit that was implemented using this equation number 2. Here this is your 2.4 volt offset, and if we can go back, this is our input was negative 2.4 volts. So in this circuit, one of these batteries, one of these voltage sources is this is negative 2.4 and this is 2.4. So one of them is your offset and one of them is your input. So let me see, this is your input and this is your offset. So first your input was negative 2.4 volts and your output was 158 microvolts, that is 158 into 10 raised to the power minus 6, or 0.000158 volts, that is approximately equal to 0. So at negative 2.4 volts, we desired a 0 volt output, and we are almost getting it. And then for a negative 1.1 volt input, the rest of the circuit will remain the same, the offset will remain the same, and our desired output was 2.5 volts, and that is exactly 2.5 volts. So implementing this circuit in both ways resulted in the same results and in the correct results that were desired. So the next example in your book, the example number 25, is your assignment. The submission deadline is 16th December, but make sure that you should devise a different solution than the one provided in your book, and it should not be just this, a difference like this. Think about it, and it should be significantly different from your book. It's not like I am including a voltage follower circuit at the beginning, or I am removing the voltage follower circuit from the beginning and now it is different, or you can just change the values of the resistances but the transfer function remains the same, or you can just take one term common and the rest of the solution is same. No, it should have to be solved using a completely different approach, and that has to be solved on paper, and you can upload the snapshots of your assignments through the Microsoft Teams. So that's it for the operational amplifiers portion. I tried to go into the details of the derivation of each and every circuit to help you understand these concepts in a better way and how these configurations work. And I hope that you would have understood these concepts. If you have any confusions, or if you have any questions, or if you have any comments, you can approach me in the office hours through the Microsoft Teams, and I'll be more than happy to answer your queries. Also, we are going to have an interactive session regarding this set of lectures on op-amps. By the end of this week, I'll announce the timetable or the schedule of that session soon, inshallah. So hope to see you soon, and stay safe, study hard, and Allah Hafiz. Thank you.